I hope this stream's running perfectly. At least that's what I hope. Yeah, we seem to be live. Yeah, that's let me check if I accidentally didn't expose anything. No, I did not. Good. Hopefully the stream's going as well. Yeah, wait, stream summary, creator dashboard. I guess that's what we're gonna head to. Home. Wait, channel. Hope this one's gonna work. Let's check it out. This one's gonna work. Let's check it out. Hello, hello, hello. Hello, hello, hello. I'm checking just if the music works correctly. I'm checking just if the music works correctly. Yeah. Though the latency is actually pretty good. Pretty good. Though the latency is actually pretty good. Pretty good. Yeah, seems like it works. More or less. Um, Twitch chat. Um, let's take the YouTube chat. And yeah, we're ready to go. So yeah, we're ready to go now. Yeah, what we did is basically move to the blocking device. We're gonna implement one interface to the bottom, basically, one interface below, because now we just, I mean, till now we worked with a FuseFS and implemented basically our own file system. With now, well, again, for a bunch of reasons, I decided to, well, I didn't scrape the old stuff necessarily, but I stored everything to the old directory, to the backup directory, so we can, again, we didn't start fresh, right? We just did a couple of certain changes so we can, well, yeah, so we can, for example, this thing's gonna be mountable as a block device, basically. So essentially a hard disk where you can install a file system on it, which you can mount as a well, virtual drive to for example, virtual machine QEMU, or use as a, oh, well, and then use which will be bootable, obviously, and use a well, or install whatever file system you want, and that's gonna be cool, I guess. So today, actually, what we're gonna be doing is we're gonna writing a certain amount of tests. Yeah, the testings I hate, but unfortunately they're necessary. So yeah, the write data and the read data. First things first. There's the block, there's the block device, write data or read data, and we can also function to bring actual size. what's this again? Actual size bytes. Here's the thing: do we actually need a? Right. We don't actually need this one. Ah, that's funny. That's funny. Because, well, just create it. And nothing's gonna happen. So we're getting data, we're just getting a bunch of zeros here. Let's um let me create from the storage. Data.clone, data.length. My English isn't very good yet, but I wanted to say I really like you to read as a programmer. You're excellent. I'm learning a lot from you. Yeah, thank you. So, thanks. Again, yeah. I mean, wait, I'm a bit too loud. Hopefully not. But, yeah. So, I'm not actually into making a lot of videos, as you've probably seen, and I actually should, because there are actually a lot of stuff to learn, which I learned at the university, which which I really would love to share. Unfortunately, I have exams soon, so that's why, for example, I'm streaming that late. It's 1:20 a.m. in at where I live. So today the whole day, I mean, I was learning. I was preparing for calculus exam, and there's a lot of stuff going on there. But yeah, one day I really probably should do like some real tutorials or real conceptual stuff, which would probably help. But thanks a lot. Yeah. Um, so yeah. Unfortunately, many guys and YouTubers are there are a lot of things which aren't explained properly. In all the YouTube videos, most of the time, they're talking about how it works and how you implement something without actually talking on why does it work exactly. And that's the point. Getting to the bottom as it is. Yeah, so we're writing data, and oh, uh, uh, data.length, same here, data.length. So yeah, again, we're doing it basically as a block device, right? Yeah, and yeah, we're yeah. So again, there's like this is pretty much the similar as the hard drive, right? There again, there are two types of devices. So any device, basically, like any device can be, is either a character device or a block device. So for example, any keyboard, any input, something we do not know the future of. So for example, we cannot guess what key is going to be pressed next. That's a character device. Any scanner, we cannot guess what value is going to come next. That's a character device. And every device we can basically random access. For example, a hard drive, we can randomly access. A certain network device, most of the time, if it's a network search, we can randomly access. a USB we can randomly access. Any storage of any data storage, whatever, we can basically randomly access it. So that's basically the main difference between these two. And any device, basically any, is either a character device or a block device. And again, currently we're working with the second one, basically the block one. So we have to embrace the random access, and there's a certain so basically writing a virtual block device, which we're doing here. I mean, we're going to be syncing it with the network, but we don't actually care about this for now, right? So what we actually have to implement is a couple of commands, is a couple of calls, which our block device has to implement. For example, it's reading a certain sector. Well, not a certain sector. We want to start at certain bytes amount. We're going to a certain bytes amount, and we start reading from them, and reading like 20 bytes or whatever. That's determined by the kernel. We don't care about it. We just have to guarantee that this implementation works. The same with writing. We want to start writing here and writing this many bytes. That's it. Well, and there's there's a bunch in new, the bunch of hours, for example. We want to flash something to drive. In this case, to our virtual drive. So unless we actually flash something, that's not persistent. It only so data becomes actually as you know, there's a hardware cache inside every SSD, inside every ATA, HDD, whatever. There's this really a chip, so it's something of a USB, which which stores the data, which temporarily stores the data, and only when we get the flash command, when the driver of the block device, or basically of a drive, gets the flash command, it really then and only then it stores the data to the persistent disk storage, whatever. So that was made deliberately to avoid constantly writing and rewriting disk and whatever. So the operating system normally manages this. Well, actually not the operating system, the file system normally manages this, when we're flashing to the disk and when we're reading, and it knows exactly there's a certain cache which has some guarantees which we also have to provide, right? So but again, now we are doing the general stuff. Now we're trying to implement the block device, the main interface. We don't care about the networking now. For now, we're just gonna do some small temporary stuff. That's what's gonna happen. Fill data with zeros for now. So yeah, basically we fill it with zeros. That's gonna be an empty one. Yeah. I hope the music isn't all the way too loud, but yeah. So again, this command, yeah. So in our case, we have certain sectors. Like actually, every hard drive, every SSD, whatever, it has sectors. Well, memory has pages, but it's basically the same concept right here. There's certain blocks you're writing. And in our case, since the system is distributed, we're gonna store everything as chunks, pretty much similar to the sectors on old hard drives, and we're gonna distribute them with a certain redundancy, basically copy it around, and yeah. And this code here, these two functions basically define how we translate the original, we're from the kernel we're getting like amounts of bytes. So for example, offset, we want to start at writing at position this and that. We don't know actually what position this is, whether it's even there or not. So we gotta calculate it, where to start basically, right? And yeah, so we're transitioning to the block index. Actually, there's something I want to rewrite about this. There's actually something I want to rewrite about this for now. There's something I don't like. Oh yeah, we're taking advantage of binary tree map. Yeah, as simple as that. Where was I? Byte offset. Translate option. Um, yep. That's a hell of a cheating, but yeah. So blocks it's key. Oh, it's the data isn't public. Yeah, to encapsulate it and secure it. Um, mm, yep, that's actually good. Right. Oh, that's a mess actually because reading data from translate from and function translate. Translate span. It's not the offset, it's a span. Translate span to block indices. Here we know vector. That within the block. Wait. So blocks indices. Yeah. So we are returning the block push block index. Yeah, we're translating to block index. So now we have to this return zeros of requested length. Yeah, that's basically what we're gonna do. Um, This indices, yes. Vector with capacity length. Oh. So, oh, you can really instantiate the vector with a certain capacity. That's cool. That's actually cool. Remaining length. Current offset is the byte offset. So, okay, we're making these variables mutable. That blocks at get index. Translate bytes to block again. Current offset. Offset within the block. Current offset size is bytes is 64. Huh. That smells. That smells. That stinks. That just look good enough. So, offset within the block. Blocks. Length, byte to read. Length, current and offset. Yeah, that's gonna work. So, yeah, again, what we're doing here is creating a vector with a certain capacity first, getting the the length from here and the current of offset, which is the offset which is obvious here. So then we are using this translate function. We are translating to what blocks we are actually reading from, right? I mean, what blocks are generally affected, and for each block, first we get the block, right? Whether it exists or not. Yeah. Okay, and here's the first error we did. Let block, this is get block. So we have to yeah, so we have to actually we have to optimize this thing from the beginning. There's this problem that if the block does not exist, we return zeros. So not all blocks are here and existing, right? So when we create a virtual drive, it doesn't necessarily mean we create all the data inside and we write it with zeros and we flood it with zeros. That wouldn't make any sense. So for example, creating 90 gigabyte of empty drive would instantly consume 90 gigabyte of memory of SSD of whatever. So that's not gonna happen, obviously. So if the zeros for missing blocks, basically doing here the same. We are basically doing here the same, right? So that's redundant stuff. Oh. Let's first current offset. Where are we using actually the block? Block size, block data. So we first initialize let's first initialize an empty vector. Oh, heck, can we? Is this even a valid syntax? Is this even a valid syntax? Let block data. Well, if there's a block, the block get. Huh? Is this really valid? Does it really work like this? If yes, I mean it's cool. That's a bit of a counter and intuitive, obviously, but let's import it like this. I don't like this imports, inline imports. So we're either reading a real data from the block, which for now we're just gonna leave it as, or we are returning a bunch of zeros. Extend from slice. Yeah, but I think we just didn't. It's not a node, it's a mod address. Not bias. Yep. There's this block device. Oh, are we actually? Yep, Redis we're running. Cool. Yeah, Redis we are running. So there's this read, which is actually which is fine. Block index, okay. Translate span. So for every block, we are oh, so we are indeed creating a new block. Okay, so new block is an index and a hash. Block index. Oh, so their functions are. Oh, yeah. I mean, unfortunately, yeah, these are. Oh shit, yeah. These for me again. These look like pipelining operations here, but actually these are like lambda functions in Rust, which is unfortunately very damn counterintuitive. Block index. So we are gonna calculate the hash, but calculate the hash later. We're even gonna mark it as fix me. Yep, that's good. So we're gonna be calculating the hash later or insert with. Wow. So there's actually again this thing. So the guys who created Rust definitely knew what they're doing. Again, I still don't necessarily like the language, but again they seem to have known what they're doing, and that's kind of makes sense. This one at least. Yeah, so we're writing the data where we created and instantiated a new block. Well, we either looked it up, or we just we'll just entry solve the blocks with entry. Yeah, I don't think we need an extra function for this one. So we either took it or created a new one. With the rest, we don't care. Well, actually, we we gotta recalculate the hash later. Oh yeah, so we didn't care about this. So actually here we have to recalculate the cache for all the blocks we're writing. For every block we're writing data, we have to recalculate the hash later. But again, we have this fixed me now for now, and again the rest for now we don't care. Huh? So yeah, so what's gonna be next? We are public function, right? Block device, right? We are writing to block device. The block we actually have already implemented, which is yeah. Now the use the error. Use. God damn it! I constantly keep forgetting how to use. Oh, it's just mod. All right. Oops. I'm just keeping forgetting the import mod of storage. So the storage loading storage module, right? Let mutable block device, right? Mutable block device equals, well, it's a new use. I hope that, again, I really don't like the imports in Rust, so I'm mute device test is equals to block device new block device. Oh, we actually don't have a proper constructor here. So we are gonna solve it. Pop and new. The ID, well, we could have taken just any random, but yeah, all right, we don't care about this now. Block size bytes, that's gonna be for kilobyte, and generation, that's just gonna be 1 for now. Yeah, for now that's just gonna be 1. So the generation is gonna be 1. The blocks are gonna be initialized as empty. Hello guys, for everybody who joined. Block size bytes is, yep, generations 1. Again, pardon me for not being proficient at Rust. I'm just learning by doing some stuff here. Logic. So basically, we pass in a new ID in amount of logical size bytes, which is in this case, yeah. So created the block device. Yeah. So hopefully that's gonna run. Nope, that's not gonna. Unit found ID and the logical size. ID and the logical size, isn't it? Self. So is it like this, right? Missing data. Where is it missing data? Oh, block. Oh yeah. Sure. Hash and then your data. Let's leave it like this for now. Actual size bytes. Where is it? Data length. Yep. Not found in, huh? Yeah, again, sorry for import problems, but new. Device. new self. What the shit? Pub fn new. So returns result, right? Yeah. Let's look at the old one. No, dash new. Log device dash new. Yeah, yeah, sure, that's gotta work. For device test. Not found in block device. Block device. That's a pub. That's a pub struct. These two are public. Guys, I believe I could need the help. Why? Just why? Let's cheat a bit on the. Let's ask this guy. Hopefully that's gonna help me. Function not found because a new function in the block is not marked up. Huh? Oh shit! I was looking at the wrong function. Yeah. Public function. Yeah. Obviously. Huh? Block device. That's new. Oh. Yeah, sure. The Rust imports. Yeah, the usual stuff. The kind of, well, the Rust imports. Yeah, I hate them. I really hate them. I gotta admit, I hate them. I really hate them. Yeah. So we just created them. Yeah, we just created the block device. We have a certain amount of logical size bytes and a block size bytes, and the generation one blocks whatever. So next thing, logical block device bytes. Okay, this one's hard coded. Oh, this one we don't currently care about, but new block. Yeah, we're just gonna leave it at hard coded. Keep pushing, broski. Yeah, thanks. Thank you very much. Yeah, again, I'm new to Rust. I'm more of a Java guy myself. That's what I learned at the university, Java and some bare metal C for Linux kernel development. Even a bit of RISC-V assembler we did. Well, there are a lot of new and cool, well, not particularly new, but cool things we did at the university, but Rust we did not. So yeah, again, we have a block device. Now we gotta run a couple of tests first. So let's read. Which country you're from? Well, that's a long story, but I live in Austria. I mean, you could hear it a bit from with the accent. You could hear it a bit because I'm speaking English with my dad's kind of making fun of me constantly because he's telling me, yeah, well, you speak English like a bit like a Schwarzenegger or something. Unfortunately, I'm not as pumped as. So yeah, we read. We got a certain result here. Yeah, let's. Let test read. Nope, we don't have to translate anything here. We just have to, well, log the device test, but read, and we just read from, well, let's say from the But offset from 0 to whatever. Your English is very good. Thank you. I'm actually my first education when I went to an international school. So I have actually four languages and Latin. So I'm my first education is actually as a linguist. Yeah. So, but thank you. Also, the university helped a lot because well, we had a huge amount of lectures in English. For example, all the networking lectures, all the cybersecurity lectures, well, German, obviously English, French, Russian, well, and Latin, obviously, but I hate the last one with all the respect to Latin. So that's from device, and we just yeah, and again, but my whole life I've been a technician. But length, right? We actually, so we can we print it like this? Oh, yeah, sure. Yeah, so we're getting zeros. So we are somewhere. Wait, let's do a commit. Move to block device architecture. Created basic offset read and write with a deterministic dynamic block creation. Yeah, so we're pushing it now. Yeah, again, so here's well, again, here's a smart thing about this thing. Well, smart, that's more of an obvious one. Again, we are not creating any blocks and we are not storing anything unless we explicitly want to write to them. Yeah. So I mean, I think that's basically pretty similar to how QEMU disk work, isn't it? Like, well, it seems well. I don't think. I mean, you could assign like 100 gigs or whatever or 1 terabyte, but as long as it's not used, that's not going to be the size of the file. I mean, even with the raw disk, not even talking about the QCOV2 or whatever the modern formats are called. But again, this thing I want to primarily make it. Well, first things first, I want to make it well. First of all, compatible with the well mountable, compatible with the Linux kernel, and most important, I want to make it compatible with QEMU, which is gonna be automatically or hopefully automatically. So yeah, we have read, we have write, but uh, uh, well, unwrap. Do we have to unwrap it? Oh yeah, we have to. It's a result we're unwrapping it. We got it. So I'll write some data. Yeah. So, oops, data doesn't match the block size. That's the first one. Oh well, first one first there. Here unwrap. It's 17 actually. So we are writing the data 1024. So that does not match the block size. No, well, that's why we're doing this test. So let's debug it. Doesn't match let's print of size block of block size with data size Thank God I have a co-pilot. Thank God I'm paying for this thing. Writing data to block 0 of block size with the data size 1024. I wanted there to well where to download. Yeah. Thanks. Again, we're I can share. I can probably share the well, the folder again where unfortunately I moved down to the block device. I wanted again the first version, well, minimal version I did was actually already compatible with files, but now it is only a block device. But again, that doesn't mean it does not work. It's not gonna work. It's not gonna be supported. So I can share the public GitHub folder, and yeah. Have a nice night and good luck. Thank you. Yeah. Yeah, it's actually 2 a.m. where I live. Yeah, so data length. Data length is not improved. No, bullshit. 2 a.m. is tough. Yeah, yeah, but I've been doing like something the whole day, and I have a sleeping problem, so I'm not tired at all. Yeah. Um, data length. Huh. Writing data. If data.length is larger than stuff.data.length, the error that exceeds the block size. Otherwise, we are overwriting it, copying from the slice, and we're slice copying it. Yeah, again, I didn't knew that there are a lot. There's a lot of smart things going on here, and there are a lot of cool functions here. I did not know that Rust has so many cool functions for the list. Well, for vectors. Sorry. Yeah, vectors is something straight out of the C++ world. That's a C++ word for well, array. Well, not array. That's well, a list, basically in Java. So writing data to block, but nothing was actually written. Self.data, copy it from slice, and okay. With the size of damn, let me pin in Rust and tell pin in Rust standard library. Yeah. Wait, what am I writing here? Vectors of whatever. Nope, it does not work here. It doesn't work like here. All right. So I believe we have to self data dot. Will this one work? Because I think that's gonna trigger a problem. No, huh? And that's the problem. Starting at 0th offset. Writing to data with 1024. That's odd. That's really odd, huh? Why doesn't it? Maybe do we have to maybe like swap pointers or something? Huh? Well, mutable self. If data.length is larger than our data, we just we do not allow it, right? Let's imagine for a second that the sectors are pretty damn small. Just for a second, right? I just want to test something, right? Let's just for a second imagine these are small. Oh, 512 bytes, huh? So it's writing data to block 2. Why didn't it write data to the block 1? Hello there. Yeah, why does not it write data to the block 1? I'm wondering. Here's the read, here's after the write. The write. Let's read like a bit more kind of. Yeah, this doesn't make, that doesn't give us like anything. I believe there's this algorithm. I believe there's this algorithmic error because it does not provide me with a it doesn't provide me properly with blocks to read. I mean to read to write into write. So translate bytes to block index. No, first things first. We have to translate to block indices, whatever. So we are writing here, and writing with block indices, right? To the block 2 and 3. Here's the problem. Why? Why are these blocks 2 and 3? I mean, I could have an idea why. Why it doesn't write anywhere here, because we're creating a new block. The block writes the data. Let's debug creating new blocks, right? Again, that's why we are doing everything locally for now. Later, I mean, unfortunately, like in the next, well, tutorials I want to say, but in the next streams, we're gonna move to the, well, network technologies. So that's what we're reading. Actually, we don't need to read anymore from here. Actually, we don't need a test read. Nothing. Creating a block device. Writing. So we are not creating anything, right? We are not creating anything. And that's the problem. Oh, oops, sorry. My bad. We are actually creating something, or hopefully at least, but you create a new block with index. Creating a new block with index 2. Also translated the block index, the right current line. Yeah, so block the block index offset within the block. Okay. So creating new block with index 2, writing data to block. Oh, first of all, for block index 2, offset within the block 0. So we don't have any well, offset, which is good. But wait, maybe it's just a temporary error. Nope, it's not. We are writing. We're writing data from 0 to, well, the offsets are making sense now. So, yeah, writing to block indices 0 and 1. Oh, do you hear me decently? I sure hope so. Maybe I'm thinking maybe for my stream I could make a like something of a stream layout or something with a chat and so on. That would be pretty cool. But one day, maybe one day. So for block index 0, we have no offset, right? We're writing from start from scratch from the beginning, creating a new block. We create a new block with index 0. Writing data to block 0 of block size 215 with data size 215, I mean 512 with data size 512. For block index 1 offset with 0, because we'll just continue writing, we create it and we write it again. Yes. So we just wrote it, and what's next? Well, write data, remaining data bytes, and the bytes to write. Huh. Write data again. Writing data block. There we don't have any. Let's just go nuclear. Let's just fucking go nuclear. Writing byte 6. Can it be just that it's a misrepresentation of something, that the debug doesn't work? Can it be just that the debug does not work? Writing byte 6 at, yeah, create a new block and we're writing the bytes again. So we are writing the bytes. I mean, we could ask the Mr. Copilot, but it's I want to figure it out by myself, because that's the point. So either we succeed or do not. Yeah. And the after the write. I mean, maybe the error I did is just like some stupid ass error. Sorry, but again, I know how it works. I know what happens, right? Data blocks. I mean, like, maybe it's again the representation. Let me Google something. Text. Is it like, well, print line is hex. Would this one work? Hopefully. Format, print line. Lazy. X. Maybe this will work. Oops. Vice test. Well, it cannot be formatted with a default formatter. Oh. Shit. Yeah, so we don't have that much actually left for some reason. Why? Why? The format display. Lock device may not arrest, does not implement a let's just rerun it for now. That sometimes works. That sometimes works, sometimes doesn't. Nope, that does not. Oh yeah, sure. Yep. Oh, output. Use format. Output. Oh, so we're getting something, but it's not what we want, right? Yeah, we're getting like 0, 0, 0, 0, 0, so we get plain zeros. Okay. Explain. I'm stupid, right? I don't know Rust. I'm stupid. Let's just let this thing just explain. Let's just I mean that it's maybe something obvious. Right, data method specifically initialized default data length for writes incoming field, but only updates the data.length byte. If data field was initialized with zeros, the remaining bytes in the data field will be zeros. That's where you see 0, 0 at the output. Um, um, if data.length is more than self.data.length, blocks data to fit the incoming data. Nope. The size of data per block is at most the size, and to be at most the size, and we're right from the start. So again, it's just the curiosity, right? Specifically, properly overwriting data field. Yeah, we are overwriting data. With zeros may not have the correct size. The loop overrides only the first byte. That's wrong because it does not. Otherwise, I would have seen here like this this first byte here overwritten. So first of all, instead of the vector, let's block here the data. Yeah, will this work? I really doubt, but yeah, again, I really doubt that that could have worked. Like, yeah, this could have worked. Oh, also, that doesn't have a compilation. So wait, fixed size vector. A fixed size fixed size vector Rust. Oh no, that's another crate. Vector and STD. No. So there's a vector of, well, unsigned integers. I mean, bytes. Yeah. New block. Data is a vector. Empty data. Yeah, I mean, that's not gonna help, obviously, but at least I hope. At least I hope. But if somebody could help me, that would be cool. Writing by 6 position. Let's ask another one. Wait, what time is it? Oh, it's 2 a.m. Okay, a bit late, but whatever. The implementation always returns zeros to fix the data. Oh, so that might be the problem, right? I kind of knew that it's something small and obvious. Because I remember I implemented. Yeah, sure. Fuck. I just told there's something like small and obvious. Length. String. Let data, and we just return it. Yep. As I told you. Yeah, there's something obvious. Fuck. Why? I mean, yeah, why was I fucking around with whether there's just this one stupid error? God damn it. Yeah, so we are writing the bytes. Do we actually let's write just a couple of bytes. Let's just pass it around and right, bytes. Hello. Six. Oh yeah, so we don't need this one anymore. Writing. Writing byte. Where's this thing? Oh yeah. Here we are writing it. So we were just misreturning, and this works just fine. Okay, let's test it. So yeah, the debug we're gonna leave for now. Module. So writing the block indices 0 for the block indices 0 for block index 0 offset within block 0. Creating new block with index 0, which is great. Well, I created this block as on demand basically. Writing data to block with data size 96. And if we want to write this like this one, then writing to block indices 1 and 2 for block index 1 offset within block 488 with size 22 for index block 2 offset 0 with starts from the beginning. Good. Yeah, so the tests basically are completed here. Have to block storage error. We're not gonna do this for now. Now we're gonna do the thing persistent as it is. Um, yeah, we are gonna do the persistent. For this, we have from previous streams. I hope, guys, please write. This the music disturb you? Because for me it's like a bit of a loud, but hopefully that's good. I can make it like, or I can change the music because it's the first time I'm trying this kind of music. Normally I had normally like synth wave and etc. So yeah, KVS 4. Yeah, Redis store. That's the load. KVS. Let's change the interface. Storable. KVS storable. Here instead connection KVS versus mutable KVS, and hopefully this one's gonna work. Public trade KVS storable. So for the block device, I mean we're gonna split the thing later. Two different files for readability. First of all, oops. Use rate manager KVS and KVS storable. Implement KVS storable. Yeah, I hope this is gonna work. Can't run, nope. Oh yeah, sure. We KVS. It's KVS storable, and it's KVS and the KVS storable. We have to well, for the object itself, manager isn't a creator root. Huh. Wait, I'm just gonna take a look at something. Yes, create manager. Sorry guys for this one, but I really have to, well, again, the import system I don't fully understand, unfortunately. Sorry for this one. Oh, so I just add the mod here. Alright. Yeah. Yes. Oops. Again, sorry guys for this ChatGPT whatever vibe coding nonsense, but again, the storage, the create systems, I really hate. It's very unintuitive. I mean, it's I read a couple of docs at the well, at the on the Rust docs website, but I still have no clue. You see, not found in the scope. Oh, public critical. Oh, oops, sorry. It's just maybe a storable. No. Self. Oh. So load the ID. Hmm. So we just reference the self, right? T.load. No, though it's actually wrong. Um, KVS store. Nope. Or the SAE were sized. And this actually key is the item. The item is a T, which should actually, well, there's, yeah, there are a bunch of generic stuff here, which really sucks in this case. Starts here. Function load. Oh yeah. Oh, okay. Yeah, sure. It's just the generics, and again, coming from Java. Coming from Java. Look device, yes. Serialize implement T. Serialize. Hard, yep, hard. Again, coming from Java with all the generics being basically native implement. Well, being natively inside the Java. Yeah, I mean, like, in Java, I could have just written like, well, wildcard implement serializable, wildcard implement comma implements, or wildcard implements serializable comma something something something. That's does not work here anymore, fortunately. So the trait serializable is not implemented for T, which is item T. That's for store, right? To string. Serializable asserted JSON. Right, serialized item. What would this thing say to me? I'm really like excited on. I mean, like again, I hate using. Oh, so it's here. KVS storable and serializable plus serializable. Okay. That's something. Asserted JSON KVS storable. Again, it should be KVS storable. What the shit? DE serializable DE. What the fuck is that? What's your architecture like? I mean, like, so here's the thing. We started a couple of streams ago. I mean, like 5 or 6 streams ago, implementing a FuseFS. Um, yeah, implementing the FuseFS basically, and partially even implemented that. So there's this all src.alt code here. But I talked to some guys who would be interested in well, running these things on a production server. And they told me, well, we would actually prefer to use a also to store a database replicas on it, and if possible, well, virtual machines. And I thought like, well, the FuseFS isn't the correct implementation for that. So I mean, I well implemented first of all the whole FuseFS with all the inodes and all the well key values in the key value storage. For now, I'm using Redis as a key value storage, although like half year ago or even like something like back then, I tried to implement my own Redis in Rust, but was not that successful. Well, I had my Redis in C++. It worked pretty good, but yeah. For now, I took Redis for specifically for well debugging purposes, because it's good to debug. There's a UI in Redis and whatever, right? And so now I am doing a and I moved down to the block device, to a mountable block device, which we're gonna do, which we are doing now. So there's basically the core is over here. Um, if you are interested, you can look up at the GitHub. I posted the link prior in the prior mess in one of the prior messages. So basically, the architecture is pretty simple. There's the block device, there's the random access, and there are well, the blocks which are gonna be sharded. The sharded, they are gonna be with a Ceph FS like protocol. Well, you would maybe ask, why didn't you take Ceph at the beginning? The answer is even if taking like tiny Ceph, which is a canonical implementation for Ceph to run it on a single node, because Ceph assumes you have like at least like 3 nodes, I believe, or actually like real Ceph starting at 5, basically. The real power you get at starting at 5, since as you maybe know, there's like a huge stack of technologies there, so it does not work alone. And generally, one of the main tasks I well I had before me is making it possible to run on a single node as fast as possible, and be able to upscale to a certain to any amount of nodes. So the blocks, they are gonna be sharded. Interestingly enough, well, I live in the EU, and we have like very strong data protection regulations. So one of the cool features of this thing is gonna be special storage policies. For example, for every virtual well drive, for every virtual block device, there gonna be a way to define where to store it, on what nodes to store it, and on what not to. So for example, this allows me to, well, and the other guys we were well, I'm communicating with my colleagues, that would allow us to well, uh, store, for example, like drives for EU customers, so they're stored explicitly within the EU and not sharded, for example, onto the US or other servers within other jurisdictions, which I believe Ceph does not fully support. And again, we assume a small and fast to maintain also storage system for block devices currently. And yeah, what I got here is basically a a block device and certain blocks. Now for testing purposes, I'm storing just data as an array inside the blocks, which is obviously wrong, which is gonna be fetched later from the nodes corresponding, calculated by the deterministic algorithm. I believe the algorithm is called deterministic scoring HRW, I believe, something like that. I mean, I looked it up shortly, briefly, but yeah, I think that that's a go for me. So yeah. And currently we were testing about the, first of all, because we have to be Linux kernel compliant. For these reasons, for example, we are, and since Linux kernel gives us all the offsets in bytes, basically not in the block sizes, although it we can advertise the block sizes as for this block device. We do actually. We currently have no real Linux interface, but we're currently just taking testing and making all the block devices like real run, right? Um, since yeah, um, but Linux kernel does not actually care about the block sizes, but about the byte offsets themselves. So we can start like writing like middle of the block, I believe. So at least from what I know. So um, there are a couple of functions here to, as you can see, translate the bytes to block index. Uh, yeah, so we get the block index and the offset within the block itself, depending on the block size. We get the blocks we're using. For example, we're writing. Well, we can. That's the testing is here in the main, so we can just like start writing at position 1000, and we write whatever data. And in our case, it's 96 bytes. So from 1000 to 1096, what blocks are generally affected? So we don't have to pull like all the blocks from the system. And if a block is affected, though not initialized, as you can see over here, and if we're reading from a block which is not initialized, we just return zeros, which isn't there. The block isn't there, and we assume it's just zeros, so it's just zeroed out. That's obviously that's obvious, right? Um, and here we create a new block. It's if we see that the block does not exist, though we want to write something into it, we create a new index. Well, we create a new block by an index. We store it in a B tree map, yeah. For now, and yeah, we're just writing data to the block, and yeah. So we just create the blocks only if written to, basically create on write. So which is, I think, the proper way to go for the for such devices and such things. I believe that's how QEMU work, how QEMU images work, how every other proper system works. Because again, like allocating a bunch of gigabytes of zeros, I mean, with all the respect, that doesn't make any sense. And first, that's the first thing, and the second thing, obviously, I'm gonna test the whole thing with real file systems and try to mount the basically real file systems and install the real file system. And I cannot just imagine having like 4 gigabytes. Again, this thing is currently stored in the RAM, and I can't just, well, imagine storing this thing in a, well, 4 gigs of zeros in the RAM. So yeah, I guess that's pretty clear. So the trade bound, there's some bullshit's going on here. From trace Redis value is not implemented for serialize, huh? Um. We actually don't have to make it KDS storable to store something like this, right? Mhm. What are these things for? TE to serialize? TE. What are these actually? I have no idea what they are doing. Method not found for T. Oh. Oops. Yeah, so T EDS storable plus deserialized. Yeah, so again, the Rust generics, they just suck. Yeah, I know they have to be determined before the runtime if possible, and on runtime if not possible. It's bound. The trade bound. Well, let this thing just explain the. Let's just explain. Explain for me, because again, these are two, actually three hardest parts in Rust. It's the borrowing stuff. It's the borrow checker, especially on distributed stuff. I mean, distributed on parallel computable stuff, on multi-threading. I mean, especially Tokyo or something. Redis commands. Ah, is this it? Huh? This isn't a generic problem. Oh, it is. That fucking is a generic problem. Yeah. The following other types implement from Redis value. Trade. Oh, so it's got to implement a trade from Redis value. Inspect. Okay, whatever that might be. Holy shit. Connection. Yeah, whatever. But why? Again, I don't understand what the problem was. I hope this thing's gonna explain, because I mean, yeah, we kind of created an extra abstraction for the set get the query. It is at CMD serialize item, so the JSON from string get argument ID query connection. Yeah, we're gonna work on this one. Yeah. Yeah, so we have a bunch of series here, but read, we're gonna read like 100 first bytes. Right, we're gonna be starting at 10. Six, for that. Huh? writing a 0, 0, 0, 0, 0 from 0 to 100. We are writing hmm. 6, 6, 6, 6, 6. Read after right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Two, 3, 4, 5, 6, 7, 8, 9, 10. Why does it wait? That should be of offset. Offset within the block is 40. So the right doesn't fully work, huh? Right data. Oh yeah, sure. The right doesn't work. Data to the block. Here's the offset. And the data. Sure. Data dot length is greater. Yeah, so here we have an offset, right? Yeah, so I just I just neglected the offset here. Right, data offset within block. Well, that's cool that I've just well looked at it. I just looked at it and like saw that something's off. Um Now we can indeed write randomly, like any random stuff. Cool. So what's next? Next we're gonna implement the load. kvs.store, kvs.load. So dot store. First of all, we gotta initialize the kvs, right? Yeah, we gotta initialize the kvs first. Simple as that. I'm just gonna take the old para code that failed to create a kvs. Failed to create a key value storage. Oops. Use create manager kvs storeable. Yep. Uh, yep, this works. Oh, that seems to have worked. Oh wait, I have well, a spammer on on Twitch. Yep, just had to. Well, we were doing advertisement. Yeah, block device one. Oh, so as you can see, we have some data written here. And we were successfully storing it. We are successfully storing the data. So well, we got at least something right here. So there's a bunch of sixes here. And yeah, again, for now, it's Redis is just for now, right? Later we're gonna be using something more of a serious one. For now, well, would you kindly stand by for sure? Sure, I'm gonna come in a few seconds back. So I'm back. Um, Here I am. I'm back. Yeah, so we have created a, well, again, KVS, key value search. Well, we haven't created anything for now. So the read works, the write works. I mean, well, let's first check if the read works. Device ID, it's one. Um, um, let's first create a KVS. KVS, I'm calling it like KVS, it's key value storage. Create a connection. KVS initialized. Let mutable device test. Block device. Load. Block device one. Oh. It's a string, right? Yep. It has to be unsigned integer. KVS dot Oh, where did we forget? Oh, yeah. Then, yeah, but we have a standard one and a return. Yeah, a couple of sixes, and yeah, block device, everything's loaded, index 0. Yeah, that's good. So I kind of like this music. What the fuck, YouTube push this content on top? Oh, hello there. Thanks. Because, well, I don't know. I'm just much love and respect, man. Thanks. Maybe because it's like 3 a.m. at where I live, and YouTube thinks that that's not relevant. So yeah, here's the thing. I really thought of like start creating videos because yeah, I've done a couple of I have a couple of old videos on my channel. For example, there was actually a bet between me and my colleague um to a six pack of a beer, a typical Austrian bet, where we well, if I can write software in something in opcodes. I mean in binary. I mean um not the assembler. I mean like the real binary. And if you're interested, you could yeah, check that out. It's I had a bad microphone. It was a long time ago. My English wasn't that good back then, but you generally would get the idea to well how this one works. Yeah, so yeah, again, now we are working on a distributed block storage, meaning it can be again in binary. That's how, you know. I mean, that's not that hard. I mean, if you get how exactly it works, it's more than doable for well for everybody. And again, it was just a challenge. So that's nothing special. But again, thank you. So again, yeah, we're working on a block device storage here, basically a virtual hard drive which can be mounted to any system. In our case, it's Linux, and Linux treats it as if it were a normal SSD or HDD or whatever we're talking about. You can install an operating system on it. You can use it as a virtual drive for a virtual machine. And it's again, it's the cool thing is it's distributed and it's fail safe. So you can, for example, that's partially what Ceph does. Is if you use it as a virtual machine drive and you boot from it, then you could nearly instantly migrate a virtual machine to another host. And again, this technology and you can boot from it, and it's a real hard drive basically, but it's distributed, it's fail safe, and it can be like mounted on every PC. It can be used on every PC, on every server. I mean, and yeah, so that's what we are doing now because with special storage policies, etc. Because it's gonna be, is it similar to Telegram storage? Not particularly, but Telegram and in the one of the core features of Telegram is pretty much similar. Yes, because it also uses this sharding. It uses this fragmentation, right? And the request I got is a certain colleague of mine uh, is doing a lot of cybersecurity for especially in storing a lot of customers' data, where it's a very sensitive one for to some extent. And here in Europe, it's basically very hard to get all the licenses. You have to comply with a bunch of rules, which is actually pretty good. Right? So. Uh, that's they are here for a reason, obviously. And he does not want to store anything on AWS. He does not want to run custom well, a custom database storages. I mean, he wants to run custom databases, but it's gonna be on one node with basically nearly a single point of failure. And he wants to have everything. How can we encrypt it? There's a lot of ways to encrypt it. The encryption I'm gonna do, I think, maybe at the end. So in my case, it's just every block we have updated, we just encrypt it. So again, we take a large chunk of data, we decrypt it using a certain key wherever it's stored. We don't care for now, at least. There's gonna be a certain key storage. I mean, I'm gonna talk to some colleagues of mine or at the university where I'm currently studying. What can be done about that? What's the good practice? What's the bad practice? And what we are gonna do is, at each block, basically, we're gonna encrypt it and decrypt it, and encrypt and decrypt at will. Also, a smart idea I came up with. I looked actually up at the Telegram. That's what Telegram using is for normal messages. As we know, normal messages, normal chats, they are not end-to-end encrypted. That would be a total mess. It would render all possible Telegram bots, communications, channels, groups, that would be basically render them unusable and impossible, and the end-to-end encryptions. So what Telegram does is basically it guarantees that a an decryption key, that the keys, or basically there are actually two keys because we're talking asymmetric cryptography here, right? So encryption is not equal to decryption key. There's a public key and there's a private key. Not related to privacy and publicity now, but whatever. So there's a key for encryption and decryption. Yeah, end to end, yeah. Well, there's Telegram also has this MT Proto and the Diffie-Hellman key exchange, which guarantees the safe key exchange on compromised channels. But again, we don't care about it now. And then not now. That's out of our scope for now. We're storing data, and there's this storage called Ceph. Again, why didn't I take it? Because that's not a storage by itself. It's a huge chunk of there's a lot of software, there's a lot of daemons there. There's so basically that's a large tower, basically a construction, right, which can store data. It can work on not petabyte, it can work on exabyte level. So it's a very high speed, extreme powerful data storage, but safer than PGP. Well, that's basically the method. It's pretty similar to PGP. Well, again, PGP is just a signing algorithm, so that's not about what algorithm you use, it's where you use it. So it's always a combination, right? I mean, there aren't algorithms, but particularly, well, more safe or less safe. Most of them are, for the most part, pretty cryptographically safe. I mean, maybe not quantum safe, but again, it's out of our scope. We don't care about it. Now, because again, that's not what we have to worry about. And I found, I mean, and there's this large Ceph technology, which well, can store a huge amount of data. Funny thing is, it doesn't work well on small amounts of data, so you have to have at least 3 servers, 5 servers. Nothing is quantum safe, buddy. No, there are algorithms which are quantum resistant. They are. In a minute, I can make a brief explanation. But the thing is, we had a special technical analysis lecture at the university where our professor did research on quantum computing. So there are algorithms which are actually quantum resistant. There are some. Yeah. It's been a couple of years just when they were invented, but whatever. So again, what we are doing here is the method I developed is basically I'm gonna develop. It's just theoretical now. It's how the data is gonna be sharded and stored. So there are possible there are a lot there are storing storage policies possible, for example, and that's we can basically guarantee what Telegram does is we can guarantee that decryption key and the data itself are stored on two different nodes. Um, yeah, so we can guarantee that with the algorithms I came up with. So I took already existing algorithms, I tweaked them around, and I hope that's gonna work. I mean, according to my analysis, theoretical observations, that's gonna work. But again, no, is it resource intensive? First of all, the algorithms we have, there's a large misconception on how a quantum computer is works. For example, many people say, well, it's so good because it can like try out all paths simultaneously, which is not correct. First of all, well, many people are saying, well, it can crack asymmetric encryption, which is based on on prime numbers. So it can basically finding a key splitting. We got a large prime number, and we have a fact. Well, and a large prime number, and we're basically splitting it. And many people say, well, it does this instantly. Basically, if you are familiar, I guess you're familiar with the so-called O notation or big O notation, which is a complexity. So O1 is basically it does that instantly in one step. So they're like basic computer steps like addition, multiplication, or like basic steps, right? And every algorithm can be obviously has a certain amount of steps, and well, again, it's theoretically everything. It's not necessarily one, but it's one step means O1 means it's just like instant. It has to do like at least or at most basically one pass through, go through the whole thing one time, and it's gonna work. The answer, no, that's not gonna work. The most optimal algorithm for prime for prime for prime number splitting. I believe that's how it's called in English properly. It's a prime number splitting. For or factorization, it's called properly, whatever. The most efficient algorithm is called a Groover algorithm, I believe. Yeah, I think it's called a Groover algorithm. So that's that's a bit of complicated one, but it's about rotating the qubit vector, rotating the quantums into specific direction, and then getting a certain and increasing that the numbers we get is the probability of we can get, then we can there's again it's look up the 3 blue 1 brown. There's a YouTube channel which he explains it like much better than I do. But there's like this specific algorithms of rotating quantum vectors, and then gaining a certain probability of getting a key, and basically a decryption key. Well, long story short, a decryption key, right? So basically, it's a number which we can use then to recreate the encryption decryption key. That's also out of the scope, but it has itself has a certain complexity, so it can't be done instantly, first of all, and second, where do you study? Well, like we here have a great environment, a great matter. I studied 2 years at the Kepler University of Linz in Austria. That's where I learned like everything. So that's where I learned it. And now I'm studying at the University of Vienna computer science, but it's by far not as exciting, unfortunately. I just moved because I'm from Vienna basically, and I just live here, and I got let's say it like this. I have some projects to do here in Vienna, and yeah, But the best for computer science studies still, I believe, the Kepler University of Linz, JKU Linz, it's called. It's where you learn like in 2 years, like a hell lot. Well, it depends on teacher, obviously, but if you're lucky, and I was hell lot of lucky, right? Yeah. So long story short, the current quantum computers are not as powerful, by far not as powerful. They have they still make a lot of errors, and they are not by far not as powerful to uh, crack even uh, basic basic no, like prime number encryption, though there there is already a post quantum encryption which is like used already, which is used in some messengers, for example in Signal, or from what I know. Again, I did not fully understand how it works. Sorry, I didn't fully understand how it works. But long story short, there is a multi-dimensional space with clouds of six-dimensional vectors. Yeah, how it? I mean, yeah, it sounds like completely overkill. Yeah, yeah, it does. It is completely overkill, and I have no idea why exactly it works. Unfortunately, the uh, this fact I'm ashamed of, that I don't fully understand how it works, but it works somehow. So there are the clouds of six dimension, from at least, again, from at least what how I understood it. There are clouds of six-dimensional vectors, and the most optimal path, like between all these clouds, the optimal path is the basically the key. So yeah, why does it exactly work? Again, I have no idea currently. Maybe I'll do a research later, because I was asked like a couple of times about this algorithm, and I was pretty ashamed. So am I now, that I do not know, that I don't fully understand it. But again, um, so, and again, long story short, this algorithm is cannot be broken, even theoretically, by the quantum computer. Well, obviously in a logarithmic time, so in a foreseeable time. I'll do this well. Yeah, that's cool. So, yeah, and again, the university to advertise the university I went to is I believe it starting at the second semester we had, for example, hacking homework. So the operating systems teacher we had, Professor Meyerhofer, who was a research PhD, who was a chief cybersecurity officer at Android. Um, and we learned exactly how Android works and why is it so safe. It is a hell lot safer now, and we learned why. And we had even hacking homework. So I can remember, like, well, a couple of years ago, I was sitting like 4 a.m. with my colleague online on Discord, and we had indeed a homework on breaking into a server illegally. It was legal, and we had to break into a university server. It was pretty easy one because it was like a basic operating systems. Um, but we had indeed this homework. Or, for example, the networking homework. The network exam, it was a hell. For example, we had to physically prove how to measure, for example, speeds of light in an optic fiber cable, or how to measure crosstalks between normal, well, RG45 network cables. Or the coolest exams we had actually for the exercise in computer networks is we were given a captured file. So basically, we were on a laptop. We could use like all the tools we had available, like ChatGPT, anything, like everything. And basically, we intercepted emails and traffic, and we had to briefly like decrypt them, and basically there were like so-called frames, which are like small packets, which any large packet or email is well consists of, and we had to pack them together, which is like actually a routine task, and we had to like basically read someone's emails to get the answers, and that was basically a capture the flag for catching some data, intercepting some data, and answering it. And we have like 15 minutes, or there were like 900 pages, some technical manual, and we had to go through it and answer some questions to it. Obviously, not manually. We had to use ChatGPT for this, and it was assumed we were going to be using something like that. So a lot of interesting stuff. And well, my favorite course was the advanced operating systems, where we learned write some, let's say, rather interesting and rather not completely legal to use software. Well, it's legally, it's you can legally write it. It's not a problem, but using it for malicious purposes, it's not. Um, Basically, kernel level exploiting, exploiting the kernel, the Linux kernel, and for example, writing a reverse shell, basically a small program, which is well, allows us remote code execution, basically start any program on the computer, but it is undetectable. Red line. What is red line? A red line stealer. Underground. Well, what's this? Yeah, that it seems. Wait, what is red line? Um, red line executes. Yeah. That's yeah. Something like red line. Well, we didn't write a panel server and backend server and whatever, but the exploit itself, it's more than doable. And not only is it doable, but it's undetectable since it loads and patches itself into the operating system, into a Linux operating system kernel. So instead of, for example, opening a connection, what does a malware, not a virus, right? But what does a malware do, right? It gotta open a connection and keep the connection open so an attacker can connect, right? That kind of makes sense. And listing all the connections would basically expose this thing sooner or later. The catch is, since this thing is running on the kernel level, it attached itself directly to the network card. On what port? We don't care about ports. We don't have any ports, because in our case, we attached ourselves directly to a network card, to a driver basically. So basically, we injected malicious code into a driver which is running as a Linux kernel, meaning we running underneath all the firewalls, all the antiviruses, everything. We communicate directly via the network card, via the NIC, and can execute any software and anything as any user or a kernel, and do basically whatever we want. And the same you could, for example, do with the keyboard stealers. Basically, you could inject and we wrote a special software, basically a driver, which was loaded with an exploit, which injected itself in between of keyboard. Well, there's a certain keyboard handler, right, which handles the keys, and the keyboard driver, right, which well, accepts the keys and reads basically the USB or whatever, the keyboard controller. And you could basically inject yourself inside and well, intercept basically everything what's going on. Like all the keys, all the presses, whatever, and you cannot detect it with an antivirus. So basically, something well, basically staying in between of handlers, of well, software and drivers on the operating system level, and you really can do that. There are certain mechanisms to avoid this, which we also exploited. We did this as well, but which there are a lot of pretty clever mechanisms. For example, like ASLR, address space layout randomization. So all the functions, for example, of the kernel are when the kernel is loaded, they're always somewhere in the other location in the memory. They're somewhere around. We don't know that where we are. We have to guess or we have to look them up. And how exactly do you look them up? Well, there's a lot of again, there's a specific advanced course where you have to know, for example, you have to perfectly know the C, the bare metal C, right? Because we're working on the bare metal level, and you have to perfectly know the Linux and generally our operating systems architectures. You like have to really know that. Got a lot of stories. I would love to see that in action. Unfortunately, I can't jump in. Yeah, yeah. Again, so that I got at the university. I got it in by accident, but I got in by accident, but there in these 2 years, holy shit! Like I learned like a hell of them. I had a hell of things there, which I learned. Unfortunately, I believe now from this starting at this year, it got like a bit worse. My colleague is still there, and he told me it got like unnecessary complicated in some fields in some subjects, but well, I believe I took the best out of it. But yeah, actually there was like one course where I even talked to the professor, and he allowed me to share the lectures and the materials online on my YouTube channel. I believe I explicitly asked him. So maybe I could I could ask the professors, etc., if whether I'm allowed to share something online. Well, it wouldn't be as exciting, obviously, but I would maybe if I'm allowed to share something online, I believe I am. Um and maybe, yeah, maybe I could make a couple of cool videos about this. So yeah. So yeah, back to this thing. I'm not gonna stream for long anymore because it's 3:30 a.m. and where I live in Vienna. Yeah, fortunately I don't have anything to do tomorrow, nor a day after tomorrow, because there's a Christmas. Huh. I just gotta learn math and analysis a bit, because that sucks. I gotta admit, that sucks. Um, yeah, so we're writing here. That works. That works. The next thing we could actually start doing is implementing um um the next thing actually we have to start is implementing the communication itself. So let me ask, just make it like this. Let's make it more. Hello, the music's gone. Let's make it more of an easy one by asking, well, I want to create a virtual block device on Linux, Rust, Linux. I implemented some functions, read write flush AC. And this one's gonna be complicated. The flush. Because until we flush to the block device, that's gotta be inside the memory. So we have to create basically a write ahead log, WAL, write ahead log, pretty much same as in the database, and only commit them and advertise and propagate it to the cluster only when well, when we were asked to. Okay, read, etc. I have to advertise the block device and the have to advertise the block device and the and its functions to the kernel. I believe it's gonna be done over socket and IO control syscall. I believe it's the IO control syscall. To you're on the right track. Concept of exact mechanism matter slot here, and then there are two common common matches. One of matches the socket IO control intuition below the canonical architecture, followed what not to do, and then how to this maps to Rust. Okay, let's read it. Maybe one day I'm gonna make even a live stream. I mean, unfortunately on Twitch nobody's watching me, but I could maybe make a live stream like the prime time or something. The correct way to create a virtual network block device. That's recommended. That's exactly what you're describing. Yeah, I know what I'm talking about here. In this case, kernel has an NBD block driver. Your program npdx uses IO control to configure block size flags. Hence the kernel socket. Kernel sends blocks requests over the socket. You implement read, write, flush, trim on optional. Well, read, write, flush. Basically, those three are the most important. No kernel module required. Stable production grade. Slide overhead in versus in kernel driver. Right. Fair enough. Simple enough. Option 2, kernel module, custom block driver, struct block device operation, request queue, make request function, requires kernel code, harder to debug. Again, from kernel development, what I know, it's not harder to debug, it's nearly impossible to debug. And it's nearly impossible to test. Rust support is experimental, obviously. NBD architecture, what you're missing, here's the exact flow. This kernel already knows how to be a block device. You only implement the backend. Cool. Step by step. Prop npd. Oh. Okay, so no error. And I guess no. Nope, don't see anything unusual, so we assume it worked. Okay, so oh, so we create a stream socket here, right? Kernel file descriptor and use a file descriptor. Oh, your Rust IO loop via the IO control. So yeah, we have to do the IO control manually. Blocks until device disconnects. npd network block device 2, it blocks until the device disconnect. Disconnect, okay. Run it in a dedicated thread. Implement the npd protocol loop. Oh, yes, so we have to even implement it with npd reply. Aren't we actually managing memory here? I mean, that's even better because device appears automatically. Yeah, No, you do not invent your own and IO control protocol. The kernel already defines it. Yeah, so at least something. NPD 0 mode empty. Yeah, didn't we have to like advertise it to the kernel with the well, NPD request magic type read write flush string handle 8 from length. Yo, whatever. Yeah. So again, I'm that's the first time I'm doing like this block device over the net NBD the network block device. That's really the first time. Traits, yeah. Tokyo NBD. Oh, so there's this async token provides trait T driver service structure. Okay, because it functions implementing a trait, right? Okay. Non-blocking, right? Non-blocking, yeah. Flush. Other possible bytes. Zeroing is special commands. Step-looking map to NPD CMD write zeros. If negotiated and supported. Yeah, that's the thing. So we're gonna go with it for now. We'll see what's or not and how it works. We'll just take a look. And again, here's the thing. I cannot do anything unless I mean, I cannot code anything. I cannot do anything unless I see the code how it should work. In this case, yeah, again, I really gotta see the code how it works. Good. Socket parents binding NBT to it is a thread. Async Tokyo loop with handles read write flush returns or anything else. Backs the device with an in-memory vector U8 so you can actually make a fast mount it. Oh, haha. Yeah, so we're backing it like this for now. Holy shit, fuck me. There's a hell load of code here. Right. I bet that's not gonna work. First of all, that let's give this fucker a try. Oh, unsafe from raw file descriptor. Yeah, it uses the raw file descriptor and the unsafe. Not good. This red spawn. This blocks until disconnect. size. Depth path. Again, I just really want to test it. I'm not hoping for anything, I gotta admit. Oh yeah, that was the first image well, I was testing the sharding algorithm with from the first stream on this matter. Docker Nix libc anyhow. Anyhow. Yep, let's loading cargo run. Oh yeah, this thing we forgot. 0. Just size 64 megabyte. Well, 1 gig of RAM, it's like it's just too much. 512 megabytes. Right. Libc. Oh, oops, it's the duplicate one. Yeah. Oops. We're gonna be fucked with all the errors. I bet. Yeah, no way that's gonna, again, there's nowhere it's gonna happen. It's compiled. Oh, did we actually? Yeah, we did. Tokyo sync. Yeah, again, I really don't understand this create system. Issues with this. Save. So remove this. Imports again. Unused imports we don't care about for now. We just wanna make it somehow run. Maybe not. Operation. Oh, so operation not permitted. Sudo cargo run. Huh. So that's gotta be compiled, right? Cargo run. Cargo run release. Well, let's just try to release. I hope that's not gonna break the system. I really hope that's not gonna break the system. Yeah, operation not permitted. Sudo target release storage. Okay. Again, guys, sorry for using the fucking ChatGPT, but again, it's the first time I'm doing such things, so please don't be mad. That's the first time I'm doing such things, so yeah. Um, if you're smoking gun out control request numbers are wrong. Zero openings control macros. Yeah, so this is the NBD set socket. NBD set socket. Feed. Socket are not set sock. So yeah, guys, I'm gonna finish the stream now. I'm gonna run a couple of tests manually myself, and hope that's gonna work. So well, thank you everybody for watching, and well, we'll see one another maybe another time. So thank you.